Thank you for joining this introductory lecture on sustainable heating and electricity. In this video, I will briefly explain some relevant trends in sustainable heating, cooling and electricity grids and highlight a couple of differences between heating, cooling on one end and electricity on the other end. The learning objectives for this lecture are to understand the differences in the current and future trends between heating, cooling and electricity, and to understand about demand response strategy in both heating, cooling and electricity. If you look at an annual electricity profile for the residential sector, this is a graph for the Netherlands, but that's typical for many countries. This profile is relatively flat throughout the year with moderate variations during the day. Whereas the residential heat demand profile has a clearly seasonal pattern, which is obvious, but it also has a strong daily pattern. You will also see that the heat demand is a couple of times larger than the electricity demand, at least in winter. If we are looking into the future, the electricity demand will rise, obviously. This is due to electrification of automobiles, electrification of heating and various industrial applications. The renewable supply for electricity will become much more volatile due to solar and wind energy. In the past, non-renewables were fully controllables, but now renewables have hourly and seasonal variations. Since all renewable electricity sources must be integrated into the power grid, the electricity supply will become very volatile in the future. The current electricity profile is relatively stable, but the annual heating profile in countries like the Netherlands has a strong seasonal component, as already shown on the previous slide. But it also has a very strong daily variation, which is illustrated in this graph. Where you see in light blue the hourly values that illustrate the large bandwidth around the daily average values. This is mainly due to the night setback. Everybody is turning off the heat supply system in the evening, turning it on again in the morning, and that is causing these excessive daily variations. In the future, the heat supply sources are baseload sources like geothermal sources or data centers that have a stable baseload throughout the year. Or these sources have a seasonal variation in the source. For example, most of the environmental heat sources have a larger production in summer than in winter, as illustrated in the graph. All the sustainable heat sources are typically relatively low temperature sources, which results in low thermal power and energy density. The limited thermal power needs to be considered if you want to apply those sources in the residential sector or in utilities. Both heating, cooling and electricity have a difference between demand and supply, both at the seasonal and daily scale. Therefore, these differences need to be matched somehow, and that requires storage. Thermal storage is really orders of magnitude cheaper than electricity storage. If you take, for example, Tesla Powerwall or a hydropower system, you get into installation prices in the order of 100,000 to 1 million euro per megawatt hour of storage. Whereas for a large-scale thermal energy storage in aquifers, for example, the price is in the order of 50 euro per megawatt hour, which is 3 or 4 orders of magnitude smaller. And at the daily scale, the building thermal inertia is available for free. For these daily variations, demand response solutions like load shifting and peak shaving can be applied, both in heating, cooling energy supply and in electricity. The daily demand response strategy for the heat supply is relatively simple, because if it's cold in winter, you can simply limit the night setback or just don't turn down the radiator at all during the night, because that avoids this excessive morning peak. Even at the neighborhood level, you can expect, as illustrated in this graph, excessive variations between the minimum heat demand in the night and the maximum heat demand in the morning. In orange, you see the daily average heat demand. This illustrates the peak shaving potential that can be achieved. Such demand response strategy is an easy win to reduce the mismatch between the heat demand and renewable sources. In electricity grids, it's also possible to develop demand response strategies, but compared to heating and cooling systems, it is much more complicated because of the renewable supply, which is highly volatile. Therefore, many appliances need to become smart appliances, so they need to be equipped with certain intelligence and communication, like washing machines and refrigerators. The domestic electricity grid also needs to communicate with the grid operator, who can temporarily turn on and off these appliances to better match the volatile power supply from sources like solar panels or wind turbines. In the end, this is much more complicated. For heating and cooling, demand response can be applied also on an individual level. So it's relatively easy to apply demand response strategies in heating supply systems. To recap this introduction presentation, there's a big difference in the current heat supply, which is highly volatile, both on seasonal and daily scale, whereas the current electricity supply is rather stable. Future electricity production, however, is highly volatile, and future supply of sustainable heat will become much more stable and at lower temperatures, resulting in this lower thermal power. Therefore, storage is essential to match the heat demand and supply. I also explained that thermal storage is a couple of orders of magnitude cheaper than electricity storage. It's much easier in a heat system to match the heat demand to the stable supply by demand response strategies than to match the demand supply in electricity grids. This concludes my presentation. Thank you for your attention.